Section 1.5 is on functions and finding equations of linear models. Part A is on functions. The definition here, a relation is the correspondence between a set of independent values called the domain values and a set of dependent values called the range values. So I want to list the domain and the range in each of these relations on this page. So the domain, notice that we can see there are set brackets around these ordered pairs. I'm also going to use those set brackets when I list a domain of a discrete set. So the domain is a set of all of the x values, the independent values, and I'm going to list them in increasing order. So I'm going to find the smallest, looks like -2, then 0, then 2, then 3. There's my curly bracket to close to say this is the set. Again, I'll just make a quick note. These little brackets say it's a set or limited number of values. Limited number of values. So I use this in the discrete case where I have a limited number of values. I'm also going to list the range, which is the set of the y values. So set brackets, and we'll look at the y values, try to list them in increasing order. So the smallest one is -1. I don't list it twice, even though it happens twice. There's just one -1 in my range, comma 3, comma 4. So there are 4 values in the domain for this relation and only 3 values in the range. We're going to do the same thing for part B. Instead of listing the ordered pairs, it's listed them in a table. We're going to list the domain. It's the set containing, it looks like -2 is the smallest, then 1, then 3. Again, I don't repeat the 1 even though it occurs in the x values twice. And the range is the set containing 0, 5, 10, and 15. All right. Now, these two examples were both, like I said a moment ago, they were both discrete. Discrete means there are a finite number of points. The next two examples are not considered discrete. These are continuous, which means that there are an infinite number of points as you connect through. You can't label just the points on dots because you go all the way in between. There are an infinite number of points. Okay, so for the discrete examples, I use the set notation and list the values. For the continuous examples, I need to give an interval. So here we're going to be using intervals. And so when I list my domain interval, I'm going to list the smallest value, comma, the largest value. And I use square brackets if I include the smallest and largest values. So I've got dots right here to indicate inclusion. So we include the smallest domain value. Domain values are x values. So you're looking at the smallest x value being -4, comma, the largest x value being +4. The type of bracket there, I only want to list the largest and the smallest, and these brackets mean that I go in between and contain these values and all the values in between them, all the x values in between them. Okay, so the range is going to be the smallest y value to the highest y value. So the smallest y value to the highest y value is going to be from -2 to 4. Don't be confused that you're not starting at this point, because this point, though it was the furthest left, the smallest domain value, this point does not contain the smallest y value that's down here. Okay, so the range values, square bracket again for an interval, and then they go from -2, comma, 4, square bracket again to close that closed interval. All right, let's look at another set of intervals here. This is also connected, therefore continuous. So I'm going to list the domain and range and intervals. Okay, so the domain is the smallest x value, which I can see right over here at -4, to the highest x value, which is going to be at this endpoint here at 5. Smallest range value, smallest y value down here at -4, highest y value up here at 4. All right. go on to the next page. Now we're talking about functions. A function is a special type of relation where each member of the domain corresponds to exactly one member of the range. There are no repeated domain members. Every element of the domain has exactly one occurrence. So I want to identify whether or not the following functions, or the following relations, are functions or not. Okay, so if you're looking at your domain values, each of these domain values is unique. Therefore, this is a function. Okay. If you're looking at the next one, though, you see that you have two domain values that are the same, two values that pair to two different range values. So this one is not a function. Not a function because the domain value 1 corresponds to two members of the range. Or it occurs twice. All right. It repeats. To make that shorter, next time we'll just say it repeats. The domain value 1 repeats. Okay. In part C and D, these are a list of ordered pairs. We're going to look for a repeated domain value. So -2, 2, 0, and 3, those do not repeat. Those all are different x values. So this is a function. Notice that we're just looking at the x values here. It's okay if the y values repeat, and in this case they do. We do have a repeated y value, but that doesn't matter in terms of a function. That'll matter in terms of whether the function is 1-to-1 or not, but it doesn't matter in terms of whether the function is a function or not. This is a function because none of the domain values repeat. All right, in the next one, looking at, I got right here already, I see 1 repeated there. So once again, 1 is the culprit. This is not a function. Oops, I can join those letters, not a function, because the domain value 1 repeats. I want to specify that it's the domain value 1 that repeats, because I can't just say 1. I want to make sure that I know that 1 is a domain value, not a range value. Range values are allowed to repeat. So it's not a function because the domain value 1 repeats. All right. In the graph below, I want to look at these ordered pairs. I believe that these are the same ordered pairs in part D. And I just want to verify visually that this is not a function. So the two culprits were these two middle pairs right there, the 1, -2, and 1, 3. I just want to show where they appear. 1, -2, and 1, 3. This one is 1, -2. That one's 1, 3. And because they have the same x value, they're going to be on the same vertical line, which leads us to the vertical line test. A relation is a function if and only if every vertical line intersects the graph only one time. Okay, this one is not a function because a vertical line touches twice. Because a vertical line passes through 2 points. So it passes through 2 points. And a short way of saying this from now on is going to be that it fails the vertical line test. That's going to be the short way for a graph. It's got to be a graph. You have to see a graph to be able to fail the vertical line test. You couldn't use the vertical line test as a reason for a set of ordered pairs not being a function, but if you saw the graph or drew the graph, you can say that it's not a vertical line, it's not a function if it fails the vertical line test because the vertical line goes through 2 or more points. All right, so I'm going to use the vertical line test to identify whether or not the following are functions. Right, so for the first one, if I'm going to be drawing vertical lines, I could draw them anywhere through here and only pass once. That means that this one is a function. However, in the next one, if you draw a vertical line right here, for example, you can see that it passes through the graph in 2 places, which means that this one is not a function. Now the explanation, not a function, is going to be both the line that you drew, so you definitely want to have a picture that looks something like that. It's not a function, and you also want to say that it fails the vertical line test as your explanation of why it is not a function. So both the picture of showing it failing, showing it hitting 2 places, and just writing a quick description. All right. The next one, let's see, I could draw a whole bunch of vertical lines, but they all only hit at once, so that one looks like it is a function. But part D, if I draw a vertical line that is the vertical line, well, it hits it in a whole bunch of places. So vertical lines are definitely not functions. It's not a function. No vertical line is, because it's vertical. It's vertical, it hits itself more than one place. All right. In example 4, I want to determine if the following are functions or not. Okay, so I'm kind of getting the idea from part C that any line that I draw, whether it's increasing or decreasing, is going to pass the vertical line test. It's true for horizontal lines also. The only lines that are not going to pass the vertical line test are vertical lines. So I can tell that this is a line that is, because the slope is positive, increasing. So this is a function. It's a function because I know that it's a line, a non-vertical line. Now this line isn't simplified. I don't have the y variable solved for, but I can still tell because there is one x and one y that this would form a line. So I know that this is a function. It's also a line. Okay, now if you remember, y equals a number is a horizontal line, so I know horizontal lines are also functions. It's a function because it's a horizontal line. And this one, x equals a number, is vertical, so this one is not a function because it is a vertical line. All right. So all diagonal and horizontal lines are functions. And all vertical lines are not functions. Go to the next page. All right, so the next couple of graphs, I have the equation and I have a picture. So I'm going to determine if it's a function or not. So quick check, drawing vertical lines to this one, no problem. Each vertical line passes through only once, so this one is a function. The next one, definitely not. You can draw a whole bunch of vertical lines that are going to fail. There's one, for example, so this one is not a function. And it's because it fails the vertical line test. Okay, part C, let's see. This one actually passes. It's a little fishy right here. It's hard to see, but those points are slightly less than 1. These ones are slightly greater than 1. So this does pass the vertical line test. This one is a function. And this one is definitely going to fail. You can see over here that this one is not a function. So it fails the vertical line test. Oops, sorry about that. All right, and the summary right here is going to be that the functions were where y was raised to an odd power, y to the first power, y to the third power, and it's not a function in the ones that have y raised to an even power. So if y is ever raised to an even power, it is not a function. Now, technically, for the odd power, it's a little bit more complicated, especially if there's more than one y present. So we can't guarantee without looking at the picture that every y odd power is going to be a function, but we can guarantee that if y is raised to an even power, that it will not be a function. All right, next page, example 6. Sketch the graph of the function whose domain is -2 to 5 and whose range is -4 to 2. That means I want the lowest of the domain, or x values, to be -2 and the highest to be 5. And the lowest of the range values, the y's, to be -4 and the highest to be 2. I'm going to kind of dot in those values. So I want my x values to have a lowest of -2 and a highest of 5. And I want my y values to have a lowest of -4 and a highest of 2. All right, so I'm working inside this little box here. I'm working inside this area here. And I can't go out or I will not satisfy one of my conditions. So I just want to draw anything that is a function. So it's got to pass the vertical line test and it can wiggle however it wants through this set. So I'm just going to start it over here, say, and I have to make sure it goes all the way up and then it goes all the way down. Okay, that is something that would satisfy those conditions. So I just want to draw anything. There's more than one answer. Let me just draw another one that would satisfy. For example, I could draw something that was a straight line and then came back up another straight line. That would do it. Or just one straight line from one corner to the other. There are lots of different ways to answer this. Oops, hold on. I didn't go all the way up to the highest point on this one, so that one didn't work. Let's say I started up here instead. There we go. Had to get to the highest point. I missed that a little bit. So anything then that goes from the highest to the lowest and from the furthest left to the furthest right will satisfy those conditions. Function notation. Okay, we know that all lines are functions, so we know that the equation y equals 3x minus 7, since it is a line, is a function. So we're going to rewrite it in function notation. Function notation replaces the y with f of x, where f is the name of the function, and the of x just specifies what the independent variable is called. So we just don't have the dependent variable anymore. We have instead f of x, the name of the function, and a statement about what the independent variable is. Okay, so I'm going to rewrite this function in function notation. I should probably change that. It seems like it's the same one, but that's okay. Any equation that has y equals can be rewritten in function notation as f of x equals, and then the equation. Okay, that's now in function notation. Okay, so on the next page, we're going to have several things in function notation. Okay, so I have 3 equations across the top. I've got an equation for the function f. F of x is 3x plus 5. I've got an equation for the function g. G of t is g of t is t squared minus 2t minus 6. And I've got a function h where h of w is w to the third. Having 3 different names, f, g, and h, is more convenient than having them all y equals and you're not sure which equation you need to use. Okay, so I'm going to take the function f. I'm going to evaluate it at -1/3. What this means is, plug in -1/3 for x, since -1/3 has taken the position of the independent variable. So in the function f, I'm going to replace the x with -1/3. So I've got 3 times x, 3 times -1/3, plus 5. And I just need to simplify. 3 times -1/3 is -1, plus 5 is 4. So the simplified answer is just 4. Okay. Same thing for part B. We're going to replace the independent variable in g with -4. So g of -4 is, okay, the independent variable t gets replaced with -4. So that's -4 squared minus 2 times -4 minus 6. -4 squared is 16. 2 negatives right there are going to make that plus 8 minus 6. So that's going to be, looks like 18. 16 plus 8 is 24, minus 6 is 18. Okay. h of -2, using my h function this time, replacing the independent variable w with -2. So it's going to be -2 cubed, so -2 times -2 times -2. So 2 times 2 is 4, times 2 is 8. 3 negatives make a negative, so -8. And in part D, we want to replace the independent variable with the expression a minus 2. So it's 3 instead of x, we're going to have a minus 2 plus 5. We replace the independent variable of x with the expression a minus 2, and then we're going to simplify. So I'm not going to get a number for this one since I have to distribute. I'm going to get 3a minus 6 plus 5 is 3a minus 1, since -6 plus 5 is -1. Okay. Parts E and F are slightly different. Instead of giving a value inside the parentheses and a value of the independent variable, they've set the equation equal to a value, so they're giving us a value for the dependent variable. So they're telling us that the equation 3x plus 5, that's the equation for f of x, should be equal to -2.5. I need to solve for x. So the first thing to do is subtract 5 from both sides. If I subtract 5 from both sides, then 3x is equal to -7.5. And then I need to divide both sides by 3 to solve for x. And if I divide both sides by 3, that's going to give me -7.5 divided by 3 is -2.5. So I end up with an answer of x equals -2.5. There we go. Okay. Part F, that's the h function, needs to be equal to 27. So the h function is equal to w cubed. W cubed needs to be equal to 27. I'm going to solve this. I need to do the opposite of a cube, which is a cube root. So if I take the cube root of both sides, the cube root of 27 will be equal to w, since that's an inverse right there. And the cube root of 27 is 3. If you're not sure how to do a cube root, it's what number multiplied by itself 3 times gives you 27. You can also use your calculator. If you go into the math menu, option 4 right there is the cube root. You can do the cube root of 27. Okay, so you do get 3. Okay, let's check out the back. I'm going to do the same thing, but instead of using an equation, we're going to use a graph for these ones. So starting off, we've got h. This entire graph is all about the function h. So we've got h of -2. So remember, this is an input value. That's an x value of -2. So I find x equals -2, and I trace down to find the y value that it's equal to. So this one's going to be equal to -4. Okay. This is the opposite. H of x is equal to 5. They're not telling me the x value anymore, they're telling me the y value. So I find where y is equal to 5, trace over and find the x value. X is equal to 4. Okay. H of 0, again that 0 is independent, that's the x value. Find the x value of 0, trace it down, that one's -3. H of x equals 0, again this time that's the y value. Y value of 0 this way. There are 2 spots where my y value is 0, so I'm going to get 2 answers for x. It looks like -6 and 2. There are 2 places where y is 0. There's 1 place, part C, where x is 0. Remember, that one is the x. Okay. Parts E and F, they just want the domain and the range. We've already talked about how to do those. This is just a review. The domain, smallest x value to largest x value. So it's going to be -6, 4 brackets, because that is a continuous interval. And the range, lowest y value is -4, highest y value is 5. Again, an interval with those square brackets right there, continuous interval. Okay, example 10, our last example for this section. Use the table to find the following. Okay, so once again, I'm using the table this time to read each of these, remembering that when I have a value inside a function, it's an x value. So g of 4 means that 4 is the x value. This is the table for x and g of x. So these are the values that are going to match up. So you plug in 4, you get out 1. Okay. Part B just wants me to do 2 of them and add them up. So g of 0, that's the x value of 0. G of 6, that's the x value of 6. So if I do each of those, g of 0 gives me -5 plus g of 6 gives me 4. If I add them up, I get -1 as the total. Okay, so I can do more than one of them, add them up, whatever I'd like to do. Part C, remember, I'm trying to find x. When g of x is equal to -2, that means that -2 is a y value. So I go backwards on my chart and find the x value that would match it. Okay. And last, what type of function does g of x appear to be? Now, this is going to be a harder question to answer, but I'm going to look at a pattern between these data points. So if I look at the pattern here, -2 to 0, 0 to 2, 2 to 4, 4 to 6, these are increasing by 2. And if I look at the g of x values, -8 to 5, that's increasing by 3, increasing by 3, increasing by 3. These are increasing by 3. Okay. If you have the same increase in all the x values and the same increase in all the y values, that's an indication of a slope. Remember, you have a consistent change in y of an increase in 3 and a consistent change in x by an increase of 2. So if you have the same change in every single x and every single y, then this is going to be a linear function. Linear function. And remember that I can write the equation if I know mx plus b, if I know slope, I already found slope, and if I know b, which is from the y-intercept. And I can see the y-intercept because I can see the place where x is 0. I can see the y-intercept has to come from the point 0, -5. So the equation for this line would be 3 over 2x minus 5. Now, it's not just a line, it's a function, so I'm going to replace y with the new name of this function, g of x. So I can write the equation for this one. We're just doing a little bit of creative thinking about this question to recognize it as a linear function. All right, that's the end of this section.